Have you ever wondered about gas hydrates? This. Before I start my presentation today, let me introduce myself. I'm Bhavani Balachandran. Today we'll be presenting about gas hydrates, a cleaner source of energy and opportunity for innovative technologies. Energy needs primarily was satisfied by using the supply of foods and the power of human muscles. The increased energy needs due to rapid growth of industries were initially by using coal and later oil and gas. The trend considering production and the use of energy lead to local, regional and also global environmental problems. When we are talking about global environmental problems, it can be actually greenhouse effect. So this greenhouse gas effect causes the concentration of CO2 in atmosphere to rise from 280 to 380 ppmp, and it same goes to methane. Concentration of methane has rise from 0.8 to 1.72 ppmp since the industrial revolutions. This enables atmosphere to trap more infrared energy and radiate it, causing global warming. The diagram above is showing the separations of carbon dioxide from fossil fuels that produces clean hydrogen and electricity. Talking about carbon dioxide, this will actually react with the fossil fuels under the sea. Methane gas hydrates is actually formed naturally below the permafrost zone and in subsea sediments. So there are actually few drilling projects which are to collect the methane hydrates, such as Lake 164 of Fortune Drilling Program, Malek 2L 38 Gas Hydrate Research, and Bottom Simulated Reflectors BSR, which was actually focusing into hydrate reservoirs. Hydrogen numbers plays a vital role. This shows the ratio of water molecules to the ratio of gas molecules. Hydrogen number is a function of the formation conditions and several values ranging from 5.77 to 7.4 for methane hydrates. So the first picture is showing molecules for methane molecules containing carbon and also for hydrogen molecules. And the second picture is showing a methane molecule with the bottom molecules that gives us a lattice structure. The first picture is showing the optimum pressure and temperature for the hydrates formations. The second picture is showing the phase formations for hydrates according to its pressure and also temperature. Basically, gas hydrates can be a problem in oil and gas industries as it can block transportation lines. It may also be hazards during oil and gas drilling and geohazards. TMHZ, which actually described as theoretical methane hydrate stability zones. So normally 1 meter cube of methane hydrates releases about approximately 170 meter cube of methane gases. It's actually natural gas hydrates are considered huge energy resources compared to normal methanes. First, methane is actually rises from dam up to GHZ. In deeper upper sediment layer, biogenic methane is released. In still deeper sediment layers, methane is created through chemical transformations of biomass at a very high pressure and temperature. When we want to hydrate energy recovery, before production we must know the spatial distributions of hydrate within a reservoir and be able to deal with water productions and disposals. Production of suboceanic and continental hydrates could have triggered RGE, runaway greenhouse effect, and contributed rapid warming at end of last glaciations that occurred 13,500 years ago. Temperature in deep oceans rise about 6 Celsius in 45.5 million years ago. Now let's move on to gas hydrates and the solutions of the CO2 emissions problem.
I will be explaining on the gas hydrates and the solution of the carbon dioxide emission problem. There are a variety of technologies for carbon dioxide capture, and the largest portion of the cost of a capture and storage sequestration scheme is due to carbon dioxide separation and compression. The fact that the most power plants use air instead of oxygen result in flue gas with relatively small amount of carbon dioxide, which is 15 to 19 moles and significantly amount of nitrogen. This makes it difficult and expensive to capture carbon dioxide as a concentrated stream, which is required in most storage conversion and reuse applications. Gas hydrate formation is the basics of carbon dioxide separation from flue gas and for carbon dioxide or H2 separation. It is noted that the gas hydrate are also a basis for removing chlorinated hydrocarbons from aqueous solution, removing hydrogen sulfate from gas mixtures, and for concentrating aqueous effluents. Firstly, I'll be explaining on the carbon dioxide separation from flue gas, a hydrate-based crystallization process that can recover 99% carbon dioxide from flue gas. The flue gas from a power plant is fed to a commercial desulfurization plant for removal of XOX. The pre-treated flue gas is passed through the first hydrator in which carbon dioxide is separated from nitrogen. The hydrate is slurried, then decomposed in a dissociator. The gas from the dissociator is compressed and sent to the second hydrator, and finally to the third hydrator and dissociator. The structure and gas distribution of the mixed hydrates of carbon dioxide and nitrogen can be studied using X-ray diffraction and CNMR spectroscopy. Next, for the carbon dioxide and hydrogen separation, integrated gasification combined cycle IGCC power plants gasify the coal, producing pressure synthesis gas mainly for carbon monoxide and hydrogen. Next, synthesis gas is either used in a gas turbine followed by capture of highly concentrated carbon dioxide or reacted with steam in sheaf reactor to produce carbon dioxide and hydrogen. Hydrogen is separated from carbon dioxide and is used to produce carbon-free energy or ammonia, whereas the carbon dioxide is available for use and storage. IGCC power plants have long been advocated for the relatively high efficiency and low levels of conventional pollutants. The hydrate slurry is then separated from the product gas and is decomposed in carbon dioxide gas and water by lowering the pressure. The carbon dioxide is compressed and may be sent for sequestration. As for the disposal of carbon dioxide, the deep ocean has by far the largest storage potential, and the concentration of carbon dioxide in the deep ocean is approximately 0.1 kg per meter cube, which are 2 to 3 orders of magnitude below in situ solubility. Carbon dioxide can be released in the ocean as a solid, liquid, or gas. The carbon dioxide changes from gas to liquid at depths below 450 meter, and it forms hydrate, which is solid, at depths below 600 meter. Carbon dioxide, also from the gas field, is stored in an undersea aquifer in the North Sea. And as for the last part, the capacity distance diagram for the transport of stranded gas that shows how natural gas hydrate-based technology or gas to solid technology (GTS) is appropriate for medium to low volumes. Methane hydrate can be self-preserved for several weeks at -10 to -20 degrees Celsius under atmospheric pressure, even though the equilibrium temperature is -80 degrees Celsius. Structure H hydrate has the maximum storage capacity and energy density among hydrate structure. A rapid hydrate formation rate is required so that the gas storage in the hydrate media can be applicable in industrial operations. Solubility and the contact between hydrate formers and water are very important to speed up the process by reducing the mass transfer resistance. Now, I'll be explaining on the hydrogen hydrate storage. It was a general perception that the hydrogen molecules are too small to fit into the hydrate cages, and no stable clatrate hydrate structure can be formed. However, high-pressure optical and X-ray studies of hydrogen and water mixtures have revealed that the formation of the first hydrogen clatrate hydrates. More recently, hydrogen clatrate of structure was synthesized and characterized. It was found that the hydrogen clatrate has an unusually high water and hydrogen ratio. The result was confirmed with a statistical mechanical model in conjunction with first principle quantum chemistry calculations. This unusually high ratio of the hydrogen to water was attributed to the fact that the hydrogen can stabilize the relatively bigger cages of water by occupying it in clusters of 2 to 5 hydrogen molecules. The hydrate forming temperature and pressure reported in the papers 280 Kelvin and 300 MPa respectively. Thus, hydrogen clatrate formation can be used as means of hydrogen storage. However, the need to operate at lower temperature has initiated a search for additives to achieve this objective. Recently, it was found that the clusters of hydrogen can be stored at lower pressures as structure 2 binary hydrate with tetrahedral. In conclusion, it is estimated that there are about 20,500 trillion cubic meters of natural gas in the form of hydrate stored in Earth's crust. This constitutes the largest source of unconventional natural gas. Unlike conventional natural gas hydrates are distributed evenly around the world. Efforts are underway to develop technologies so that some portion of this resource becomes a reserve. The development of analogy with coal-based methane is invoked to estimate that within 20 to 25 years, recovery will begin. On the other hand, dissociation of these naturally occurring methane gas hydrates and release of methane is in the atmosphere and has the potential to cause a runaway greenhouse effect. Such a drastic global change that has occurred 55 million years ago as well as 13,500 years ago. Gas hydrate formation is seriously considered as a platform to develop clean technologies. Technologies are being investigated are CO2 separation from flue gas, and from CO2 and H2 mixtures, natural gas transport and storage, and finally the hydrogen storage. Thank you.